Hey, did you know that every planet in our solar system has a secret? Well, actually, all 8 of them do. Today we're going to talk about ellipses. Okay, so we're just going to cut right to the chase. What if I told you everything you thought you knew about planets orbiting the sun was wrong? We're not just talking about simple circles here. Get ready to dive into the mind-blowing truth of each planet's unique elliptical journey and discover how these cosmic dances might secretly hold the key to understanding alien life. We usually like to think of planets traveling around the sun in perfect circles, and that makes sense, right? That's what we were taught. But in reality, the path that each planet travels along is anything but simple. Okay, let's rewind a little. Thousands of years ago, our ancestors looked up at the night sky and saw the moon traversing this perfect circle across the sky throughout the course of a year. At that time, it was assumed that the sun also traveled in a circle, and since it appeared larger than the moon, it must be much farther away. Then, when the moon passed between the Earth and the sun during a solar eclipse, it was concluded that the moon must be roughly the same size as the sun, just really far away. This way both could fit inside that perfect circle. And then along came Copernicus, Galileo, and Newton, who revolutionized our understanding of the universe by showing that it was actually the Earth that was revolving around the sun and not the other way around. Our picture of the solar system became forever altered by the heliocentric model, and it was now clear that the Earth's orbit had to be circular. After all, circles are perfect. They represent order and balance. Chaos only exists outside of them. But wait, there's more. In the late 1800s, an American astronomer named Abbott Lawrence made a discovery that shook the scientific community to its core. Using precise measurements, he determined that the sun wasn't exactly in the middle of the planetary orbits as previously believed. Instead, it turned out that all the planets orbited the sun in slightly squashed circles, slightly tilted relative to one another. So what does this mean for us Earth dwellers? Does the fact that our sun isn't in the middle of the planetary orbits mean that we're doomed? Will we all be flung into outer space? Or will we fall straight into the scorching hot furnace of our sun? Or maybe it doesn't mean anything at all, and we should all just go back to believing that the Earth is the center of the universe. Well, don't worry, because today we're going to dive into the science behind this phenomenon and discover why it actually doesn't mean any of those things. We'll also learn how this discovery helped scientists develop the theory of general relativity and what it means for the possibility of life elsewhere in the universe. So stick around and let's unravel the mystery together. First, let's talk about how we figured this out in the first place. Back in the early 1600s, an English mathematician and astronomer named Johannes Kepler developed 3 fundamental laws of planetary motion that explained how the planets moved around the sun. These laws were based on detailed observations of the planets made by Tycho Brahe, a Danish astronomer who came before him. Kepler's first law states that planets move in elliptical orbits with the sun at one focus point. Now remember when I said that planets travel in circles? Well, turns out they actually travel in slightly squished versions of circles called ellipses. An ellipse is basically a stretched out circle where the length and width are different. Eccentricity is a number that ranges from 0 to 1. If the eccentricity is 0, the ellipse is actually a perfect circle. But if the eccentricity is closer to 1, the ellipse becomes more stretched out, looking more like a comet tail. In fact, comets have an eccentricity greater than 1, and their paths are technically hyperbolas, which are like squished circles that extend infinitely. So if the sun is at one focus point of the ellipse, that means it's slightly off-center. But don't worry, it's not like the planets are whizzing by the sun super close all the time. In fact, they never even get close to the other focus point of the ellipse. Now you may be wondering, what's a perihelion? That's when a planet is at its closest point to the sun in its orbit. And what's an aphelion? For Earth, the perihelion occurs around January, when the Earth is about 147 million kilometers from the sun. And the aphelion occurs around July, when the Earth is about 152 million kilometers from the sun. Now that we've got the basics down, let's see how each planet's unique elliptical journey affects its relationship with the sun. First up, we have Mercury. the smallest planet in the solar system. Mercury has an eccentricity of 0.206, which is pretty high compared to the other planets. This means that its orbit is quite elongated, and its distance from the Sun varies significantly throughout the year. When Mercury is at its perihelion in January, it's about 46 million kilometers from the Sun. But by July, it's zoomed all the way out to 69 million kilometers. During its perihelion, temperatures can reach 430 degrees Celsius, hot enough to melt most metals. But when it reaches its aphelion, temperatures can plummet to negative 180 degrees Celsius. That's a swing of more than 600 degrees. No wonder Mercury isn't known for its pleasant weather. Next, we have Venus, which has an eccentricity of 0.07, which is almost zero. This means that its orbit is nearly circular. In fact, Venus is the only planet in the solar system whose orbit is fully inside the Earth's orbit. Because of its high atmospheric pressure and thick clouds, Venus is incredibly hot, even though it's closer to the Sun than Earth. Temperatures on Venus can reach 370 degrees Celsius, hot enough to melt lead. All right, now let's take a look at our home planet, Earth. As we mentioned earlier, the Earth has an eccentricity of 0.017, which is a bit higher than Venus, but still pretty close to zero. This means that our orbit is not perfectly circular, but it's not too far from it either. The slight tilt in Earth's orbit causes the seasons we experience throughout the year. When the northern hemisphere is tilted towards the Sun, it receives more direct sunlight and experiences summer. Meanwhile, the southern hemisphere is tilted away from the Sun and experiences winter. As the Earth moves through its orbit, the amount of solar radiation it receives remains relatively consistent, allowing for the development of stable climates and oceans. Next is Mars, which has an eccentricity of 0.093. This means that its orbit is a bit more elongated than Earth's, but not as much as Mercury's. Mars has experienced significant climate change throughout its history, possibly due to changes in its orbital parameters. In the past, it may have had a thicker atmosphere and more liquid water on its surface. However, as its orbit shifted, the amount of solar radiation it received decreased, leading to a colder, drier planet. Scientists believe that understanding the changes in Mars's orbit over time could help us predict its future habitability and search for signs of ancient life. The exact reason for the shift in Mars's orbit is still unknown, but it could be due to gravitational interactions with other bodies in the solar system. Studying these interactions could help us better understand the dynamics of our solar system and the forces that shape planets' orbits. Now let's look beyond our solar system to exoplanets orbiting other stars. Some exoplanets have been found to have highly eccentric orbits, while others appear to have nearly circular orbits similar to Earth. The range of eccentricities observed suggests that a variety of orbital mechanisms are at play. For example, planets that form closer to their star may experience stronger gravitational interactions that result in more circular orbits. Meanwhile, planets that form farther away may have more eccentric orbits due to weaker interactions. By studying the diversity of exoplanet orbits, scientists can gain a better understanding of the processes that shape planetary systems and the factors that contribute to stable, long-lived systems. And as telescopes like JWST come online, we're starting to gather more data on these exoplanets and their orbits. With more data, we can start to see trends and correlations between the properties of the star and the planet and their orbital characteristics. This will allow us to better understand the physical processes that govern the formation and evolution of planetary systems and the factors that determine the stability of these systems over billions of years. Understanding these concepts is crucial for the search for extraterrestrial life, because the distance from a planet to its star has a major impact on its potential for habitability. For example, if a planet is too close to its star, it may be tidally locked, meaning that one side always faces the star and the other side is in perpetual darkness. This could create a harsh environment with extreme temperatures and limited places for liquid water to exist. On the other hand, if a planet is too far from its star, it could be too cold for liquid water to exist at all. But if a planet is just the right distance away from its star, it could have a decent chance of supporting life as we know it. But even if a planet is in the habitable zone, its orbit can also affect its habitability. If a planet has a highly eccentric orbit, it could experience extreme temperature swings throughout the year, making it difficult for life to thrive. But if a planet has a circular orbit, it could have a more stable climate, making it more suitable for life. The discovery that the Earth's orbit is slightly elliptical and tilted helps us understand how these factors interact to create the conditions for life as we know it. By studying other planets and exoplanets, we can learn how variations in orbit and axial tilt affect the development of life and whether certain conditions may be more conducive to its emergence. One way we can study this is by looking at the atmospheres of exoplanets. By analyzing the light that passes through their atmospheres, we can look for the presence of certain molecules and gases that are indicative of life, such as oxygen, methane, and carbon dioxide. For example, if we detect large amounts of oxygen and methane in an exoplanet's atmosphere, it could suggest the presence of a liquid water ocean. This is because oxygen and methane are unlikely to occur together on planets with an atmosphere unless there is liquid water present. By looking for these kinds of biosignatures in the atmospheres of potentially habitable exoplanets, we can gain insight into the conditions necessary for life to flourish. We can also study the climates of exoplanets by looking at their surface temperatures. If an exoplanet has a relatively stable and Earth-like climate, it could be a sign that it is habitable. By studying the climates of other planets and exoplanets, we can better understand the range of conditions under which life could survive and identify the factors that make a planet suitable for life. Overall, studying exoplanets and their orbits helps us better understand the conditions necessary for life to thrive. By learning more about the diversity of planetary systems out there, we can gain a better appreciation for the uniqueness of our own solar system and the delicate balance of factors that have made Earth the only planet we know of that can support life. So keep looking up at the stars and keep asking questions. You never know what you might discover. And thank you for joining me on this journey of discovery. If you enjoyed this video, please don't forget to subscribe and leave a comment below. I'd love to hear your thoughts on what we've learned today and what you'd like to see us cover in future videos. Who knows, your comments may even inspire our next adventure in space. Until then, keep exploring the wonders of our universe and all the secrets it holds. Thanks for watching, and as always, keep looking up.